Okay, we're going to take a couple of minutes before we see the next lab, not to do anything hands-on, but to just see what's involved if we wanted to do this with Internet Explorer 11. I don't know how many of you here care, but in my company we do care because there are a lot of people that are going to keep using Internet Explorer for years to come, and actually have good reasons to do so. Their organization has created internal applications that only run under IE. It takes those organizations a long time to replace those applications. So they have upgraded IE to the latest supported version, which is 11, and they're going to keep using it for a while. The problem is that although IE has a pretty good web crypto implementation, it's not quite the same as what we've been using. It's based on a 2-year-old version of the spec, not the candidate recommendation. And the main reason for that is it doesn't use promises, which is necessary because IE 11 doesn't have promises in it. Instead of using window crypto subtle, use window MS crypto subtle. It's prefixed. Instead of returning promises that have methods for then and catch, it returns key operations and crypto operation objects that have properties for callbacks for on success and on error. So here's a summary of the differences. We see here on the left in the standard, subtle is called window.crypto.subtle. On Internet Explorer 11 is called window.mscrypto.subtle. Generate key, on the left we return a promise, on the right we return a crypto operation object. To use that resulting promise, on the left we just invoke the then method and pass it a handler for success. On the right we actually specify a callback for the on success property. And it's a handler, and instead of being given the actual result, it's given the event that the operation is completed, and the events.target.result property is the actual result. Same thing for error. Instead of using catch, you set on error to a function with the event. The error message is event.target.result. So to convert lab 1 to IE 11, it's pretty mechanical. The main thing is, although you can chain promises, you cannot chain callbacks. So it's a little clumsier code, even though the steps are the same. So let's take a look at that in IE. There we go. There's IE. Generate key. Encrypt it. Creates an IV and ciphertext. Decrypt it, we get the plain text back. It's interoperable. You can take the IV and key to the other browsers and use them, and the plain text and ciphertext can be shared back and forth. So to take a look at this solution in Lab 1 variant, instead of having promises we can chain, we return an operation, in this case a key operation, as a result of generate key. And instead of using then and catch, we have an on complete handler, and later we have an on error handler. Now, after the generate key is finished, we need to export it. We can't really return that export. It's not like a promise. So we have to have the handler for those, and that's nesting. So we do get a lot of nesting when we use these callbacks. But other than that, it's line for line the same, except for getting the value out of the .target.result property instead of being given the value directly. Works the same way. I think this is a nice reference if you need to support it. You do need to usually create a different version of the code. It is possible to use a promises shim, a promises polyfill rather, for IE 11. And I wrote a little shim that lets you use a lot of the standard crypto functions syntactically the same as an IE. It just wraps them so they look like they're running the same way, even though under the hood they're different. There's enough subtle differences that you can't do that for the whole API, but I was able to do it for the parts of the API I needed. So it's possible to do this. It's probably worth doing it. Yes?
So here, when you export the string, and then you're importing it to the decryption, you and I just discussed when you create a crypto key, you can specify, okay, this is good for encrypting and decrypting. But what you just did there ended up generating the key, right? You imported that key from the raw string. Instead of keeping that key.
That's right. After we generated the key in both these examples, the IE 11 example and the standard example, we created a crypto key and we threw it away. We created the crypto key, we exported it, we kept the exported version, but we threw the actual crypto key object away. So when we needed to encrypt or decrypt, we had to create a new crypto key by importing it. And the new crypto key that we used just for encrypting and then threw it away, or just for decrypting and then threw it away, could be created for more restricted uses if we wanted to, which in the example we did. Not that it really made much difference. We could have put the other values as well. Okay, these two labs were a good way to get introduced to the API, but it's not very practical. If you want to send secret messages to somebody else, you're going to have to, first of all, share the key secretly and go ahead and call them and whisper to them a 256-bit random number. People aren't really good with that. They want to use a password instead. So the next lab is going to tell us how to create a key, reasonably good key from a password. If the user's password is the word password or the string 1234, you're not going to get a really good key out of it. Somebody's going to guess that choice. But if the user picks a good passphrase, we're going to get a good key. We're going to do a couple of other things in this lab too. Instead of producing in a form base 64 encoded ciphertext and a hex encoded initialization vector, we're going to actually read the original plain text from a file and produce a file as output that you can just pass to somebody. In this way, for example, instead of just working with text back and forth, we'll, in our example, work with a photograph back and forth. So why would you want to derive a key from a password? Because people aren't good with big binary numbers, or even hex numbers, which seems so user-friendly. That bothers a lot of people. So they want to share a password, and so our problem here is given a password, get a key. The goals for this lab are going to be to derive a 256-bit AES CBC key from a user set provided password or passphrase. Then we're going to encrypt plain text that we get out of a file with it, and we're going to package the IV we created and the ciphertext together in a single file that we download back to the user. And then we'll reverse it. So in addition to the crypto, well, let's take a look at this, and then we'll talk about what we need in addition to crypto. Okay, so for password-based key derivation, very secure passphrase. We want to encrypt a file using that passphrase, so there's a photo. Encrypt it, and the file gets downloaded here. And there's the file in my download folder. To decrypt it, I choose the ciphertext file, the encrypted one. Whoops. It couldn't decrypt it because I tried to decrypt the source file, and the source file wasn't encrypted first. Didn't really intend to show that error, but it's useful. So instead, let's go ahead and pick the ciphertext output from the previous operation and say decrypt it. And we get a file back that if we try and open it, Windows is not going to know what to do with it. If you're running under Linux or I think a Mac and you just double click this, it's going to open the image. It's going to figure out it's an image. For Windows, we've got to give it a hand and tell it it's an image by changing its file suffix. But there we have the output and our photograph comes back. So this is a lot more usable than our last one where we had all that stuff, hex and base 64 encoded in the form. By the way, these file names, the way we set the file up for download, it's up to the browser what to name the file. We have no control over it. And Chrome tends to use UUIDs that are long and opaque, no file suffix. Firefox tends to use shorter, little base 64 encoded strings. You just don't have any control over it. There are ways in JavaScript to provide a file for download that you can control it, but that's not really part of the crypto API, so we're not going to spend time on that. All right, so how are we going to do this? Well, a password is just a string. Let's just take the first 256 bits of that string and say that's our key. And if it's too short, let's add a bunch of zeros. That's not a good choice. It's very, very easy for somebody to try a lot of different passwords and very quickly try a lot out, do a dictionary attack. So we might take a hash of the password. That's a lot better, but not great, because you're not slowing down a dictionary attack by much if they have to just hash the guessed passwords the first time. So you can use a salt, and that helps because your application has a different salt from anybody else. A salt is just a string you've picked. It's not a secret, but it's different from other people's strings. And that means somebody can't take a pre-computed list of guesses and use it, but it still doesn't take them long to guess. No, the correct solution is to use an algorithm specifically designed for this purpose, known as a KDF, or key derivation algorithm. They operate by being given a password or passphrase, creating a key in a way that makes it hard for reversing it to get the passphrase back, or guessing it with a dictionary attack. The typical method is to do repeated salted hashes, just so that if somebody wants to do a dictionary attack, it's just too slow. There are 3 different algorithms that are available in subtle crypto: concat, HKDF-CTR, and PBKDF2. HKDF-CTR was just renamed by the Web Crypto Working Group yesterday. So the next time the spec is published, it's going to just be called HKDF. However, we're going to use PBKDF2. And that's because I'd used it before and I was familiar with it, and because it's supported in all the browsers I work with except for Microsoft Edge. So this is one example that's not going to work in Microsoft Edge yet. I think they're definitely going to support it, they just haven't gotten around to it. One weird thing about PBKDF2, in fact for all these key derivation algorithms, if you look up the specification, it says in order to derive a key from a password, first provide a base key, which drives me nuts because I've got a string that's my passphrase. Where's this base key come from? Well, after a few days of banging my head against the wall, I realized that the base key is essentially just a crypto key object that has the password inside of it. It doesn't do anything to transform it. It just makes it syntactically the format that the API insists the parameter be. So we're going to need to get the base key from our password. Then we're going to provide a salt, and we're going to tell it to run this algorithm to give us a actual good key out of it. The iteration count, how many times it should run this algorithm, should be high. When the algorithm was first proposed in 2000, they said do 1,000 rounds. We're going to do 1,000,000 rounds. Computers keep getting faster. Now, one interesting thing, I mentioned that the native libraries were faster than JavaScript. PBKDF2 is an algorithm that is available in JavaScript, a pretty well-respected JavaScript library called the Stanford JavaScript Cryptographic Library. And I actually ran this with 1,000,000 iterations using the Web Crypto API. It took a blink of an eye. I couldn't even see a delay. And then I ran it with the pure JavaScript library, and it took 5 or 6 seconds. So you do get a much faster operation with native code. We're going to use 4 methods. The first thing we need to do, well, what we want to do is use derive key, but we can't do derive key until we have our password converted into a base key. So we're going to use import key to convert our password into the base key so that we can then use derive key to actually convert that password into an AES CBC key. Once we've done that, we're going to use encrypt and decrypt. To do this example, the reason we didn't do the stuff with files before is you need to know how to manipulate files in JavaScript. We're going to use the file reader object in the DOM. That lets the user select a file in a form element, and then JavaScript can read that file into an array buffer. It doesn't use promises, just a traditional callback. So we're not going to try and do asynchronous operations in parallel. We're going to finish dealing with deriving the key, then we're going to read the file and use the key we derived. We're also, to get the array buffer out, the ciphertext out, we're going to put it in a blob object. That's also relatively new in JavaScript. You can create a blob object from an array buffer or from a sequence of array buffers. You can concatenate them and get a URL for the blob, which you can then tell the browser to download for the user. So, the steps for derive key. Whenever somebody clicks encrypt or decrypt, rather, that's when we're going to do our key derivation each time. So the first thing we're going to do is the key derivation. Then we're going to kick the file reader off. Then when the success handler is invoked by the file reader, we'll have an array buffer of plain text. We'll just encrypt it the way we did before. And we'll create a single blob from the 16-byte initialization vector followed by the ciphertext, get a URL to that blob, and download it to the web page. We have 4 minutes before the break, so you can get started on it now. During the break, Lori or I will stick around the whole time, and we will be back here at 11, And we'll have another 5 minutes after that to let you fiddle with it, and then we'll go over the solution then. Thanks. Before we actually get into going over the solution, I want to go over how the application works again. What I've realized from some of the questions is that I focus so much on minimizing the steps the developer had to do that the user experience isn't as clear as it might be. So if we go look at the password-based key derivation, what we're doing here is we're putting in a passphrase, choosing a file, encrypting it, and getting a file back. Now, immediately we want to decrypt that file to see if it round trips, to see if it worked properly. But if I click decrypt right now, it's not going to decrypt the file it just created. It's going to try and decrypt the file that is in my file selection box, which was the original plain text. If I try and encrypt the original plain text, it is not going to work. It's not in the right format. So when I'm ready to decrypt, I need to choose the output file from the first operation. Now I can decrypt it and get it downloaded and look to see if it matches byte for byte the original file. The same thing is kind of true on lab 1, where it wasn't obvious that when we decrypted, it took what was in the ciphertext box and filled in the plain text box instead of going the other way. The other thing that wasn't too clear was why we want to do this. I'm going to talk about that in a minute. Well, actually, I'm going to talk about it right now. Why would we want to do symmetric encryption? The problem is symmetric encryption really carefully secures your secrets, provided you know another secret, the key. And if you want to communicate with somebody else, you're going to have to share that key, in which case you might as well share the secret the same way you did originally. What's the good of having a key? Well, for example, suppose you were 50 years ago a Soviet spy. Well, what you might have had is some agent secretly work their way into the country and secrete a key in a hollow rock in the middle of the garden in front of the Lincoln Memorial, perhaps. You went and got that key, and now that you have the key that your handlers back at home use, you can communicate securely. You had a mechanism for securely sharing the key. Sharing the key is the hardest part of cryptography, key management. It's harder than the algorithms we've done. Password-based key derivation makes it a little bit easier, although it's still difficult if you're sharing a key between two people. Public key cryptography, which is what we cover in labs 3 and 4, makes that much, much easier. But there still is a really important use case for something like password-based key derivation and symmetric encryption. I use this to store all my passwords for all my different websites. I remember one passphrase. I have a file that has all the passwords in it, and I encrypt it using that passphrase, and that encrypted file is what's on my PC. Now when I need to know one of my website passwords, I use my passphrase that I never had to tell anybody, it's only in my head, and I use it to decrypt the file back and get the website password back. I also do that for my credentials, my SSH keys, things like that for actual sites I manage. So there, I use a very good passphrase. One of the main passphrases I use is, I think, 40 characters long. So something I can remember, but not something I'll share with anybody else. Something that's going to be hard for somebody to crack. So that's a good use for symmetric cryptography, is to encrypt something for yourself for later use. A lot of people use cryptography because they're required for security to have data stored encrypted. So they encrypt all their files, and then they've got to say, well, we need to remember the key, and so they put the key somewhere else on the same system with the encrypted files. I went to a session at Amazon that talks about key management, and they have a technical term for that kind of operation, storing the key on the same system as the encrypted files. That's known as encryption. It doesn't really secure anything. So we're going to take a look at the solution for password-based key derivation, and there is a use case, namely for protecting stuff for yourself, or maybe one person you can secretly meet with and share that key with. And then we're going to see the magic of public key cryptography that actually opens up the world to a lot of other uses. So lab 2 solution. There are 2 buttons, encrypt and decrypt. Encrypt file, when we click it, is going to look at what file was selected in the form element, read that file in, create a key from the passphrase you entered and use that key to encrypt the file. Decrypt is basically going to do the exact opposite. It's going to select the file, read it in, and use the key derived from the password to decrypt the file instead of encrypt it. So since the first thing we do in each of these cases is to get a crypto key from a passphrase, instead of repeating that code twice in my solution, I wrote a separate function called convert passphrase to key that, given a string that is your passphrase, will return a promise that will yield an AES key, since encryption and decryption both need to do that step. So I'm going to scroll down. And see how that works. That's the thing that does derived key. So we know that to do PBKDF2, we have to have a specification of a number of iterations. We'll pick 1,000,000. We need a salt that our application uses that nobody else uses, so I just threw up a string together. Since I put that in as a string, I need to convert that to a byte array, so I used one of the utility functions to convert that to a buffer. And the passphrase is going to be something I use in the Crypto API to eventually end up with a key. All data that's coming from outside the system has to be in array buffers, so I'm going to also take that string and convert it to a byte array. Now, once I get past these first 4 lines, I'm ready to derive the key. Deriving a key from a passphrase with the Crypto API is 2 steps. The step you care about is the derived key method. But the input to the derived key method is a base key that is itself a crypto key. That base key has to represent your passphrase. So that's the first step, is to get the base key. So we're going to do an import key, taking the passphrase bytes as raw input. So that's the format. We're going to create a key that's useful for PBKDF2 only, and the operation it can be performed for that key is derived key. So we create this base key. It's not a cryptographic key. It's actually just an object that the API uses that has the passphrase inside of it. And the reason we do that is that the method for derived key requires as its input the algorithm specification, which includes the salt and the number of iterations and what hash to use, the base key, which represents the passphrase, and then parameters that tell us what key we want to have come out of it. Those are the same parameters we used for generate key and import key before. Now, we're not going to have to make this key exportable, because we can rederive it from the passphrase in the future if we need it. So no point in making it exportable. The other thing is, if I'm going to do encryption, the key I derive only needs to have as its usage encrypt. If I want to do decryption, it only has to have its only usage being decrypt. Since I wanted to have one function, it's the first step for both encryption and decryption, I simply have my import step say that the key can be used for both operations. One question a lot of people have asked is, what does this do if I restrict the usages? And the answer is, it's just a notice to the API as to what it's going to do when you ask it to. It doesn't actually affect anything about what the key itself is. It just puts a restriction in the object, so the API will say, hey, you created the key, you said it was for decryption, now you're asking me to use it for encryption, and I won't do it. I just won't, because that's not what you declared you wanted it for. Doesn't mean it's a different key in any way, shape, or form. All right, another thing to look at is notice that the hash I'm using for the repeated operation is SHA-1. That's because Firefox, which is an important browser, currently only supports PBKDF2 with SHA-1. So that's good enough. It still does a good job of driving a key, and we catch the errors and we return that promise. Now, once we get past that, the rest of the operation is essentially what we saw before, except we're going to work with files. So once we've got the passphrase, that yields an AES key. So we get the file element in the form, and we get the file object, which is the first thing in the array that file element has. Create a file reader object, set up the success handler, and then after the success handler, further down, we kick it off to read it as an array buffer. What this will do is it'll have the reader actually read the file into an array buffer, and when it finishes, it will invoke the onload function. So the onload function is going to get the plain text byte out of the result of the reader object, and it's going to get the IV by creating a brand new IV randomly. Now that it's got an IV and a key and the plain text, all those 3 things, it can do encrypt exactly as we saw before. But the result of the encryption being the ciphertext buffer, we're not going to just base64 encode it and put it in a form element. Instead, we want to download it to the user. So we're going to create a blob object, and the blob object is going to be created by taking the 16-byte initialization vector, followed by however long the ciphertext is, creating a blob out of it, making it an application octet stream MIME type, and getting a URL. The reason we want that application octet stream MIME type is so that our web browser doesn't try to display it. It's just gibberish. When it sees application octet stream, it's going to just download it. So we get the blob URL, and we set the browser's window location to that URL, which will force the browser to download the file. Okay. Decrypt is almost identical. It gets the passphrase and uses that helper function converted to a key. Then it sets up the file reader. And the only difference is, in the handler of the file reader, instead of creating a random IV, it's going to get the IV as the first 16 bytes of the file reader result and the ciphertext of everything after byte 16. That's it. Then it uses a decrypt operation that gives us a plain text, it puts that in a blob, and forces it to be downloaded. Now, to my mind, password-based key derivation is really only useful for people keeping secret files for themselves. They don't have to share the password with anybody. They can store it on their machine. They can store it in the cloud. And if the file's compromised, it doesn't actually mean the information in it is compromised. And there are a lot of uses for it. Do any of you use LastPass to store your passwords or any other kind of password vault? They basically all work this way. They take a passphrase that only you know and use it to create a symmetric encryption key and encrypt your passwords with that. But for practicality, we want to go a little bit further. So we're going to dip our toes in that with the next lab, which is digital signing and verification. What's a digital signature? A lot of people think that a digital signature is a picture of your written signature that's appended to a file. But that's actually really quite useless, because anybody who's ever seen your signature can copy that and append it to any file they want, and that doesn't mean you've actually signed the file. So what a digital signature is a piece of data that's derived from the file and a key that can show that the signature was created from that file and key. Any other key, any other file would not have created that signature. Verification is the process of checking that fact, that the signature you're given actually could have only been created with the key and the file. That way, if somebody digitally signs something and a year later says, I didn't create that file, you can say, well, we got a signature. The signature is for that file. So you say you put in a file that you were going to pay somebody $50, but the file says you were going to pay him $5,000. Well, we can prove the file wasn't changed. When it was signed, it said $5,000. And we can also prove that the file was signed by the person who knew that key. So the basic logical mechanism to sign it is you take a cryptographic hash of the file and you encrypt it with the key. The encrypted hash is the signature. When somebody wants to check it, they're given the file and the signature. Well, they do two operations. They do their own cryptographic hash of the file, and then they take the signature and they decrypt it with the key and see if that matches the hash they just got. If the two match, then it's a proper signature. There's a huge weakness with this approach, with what we've learned so far, though, and that is for somebody to verify a signature, they have to know the key that was used to sign it, which means they could forge the signature. The use case my company has is, again, I mentioned with sealed bidding. But one thing that happens if you want to build a highway and you want to submit a bid to a DOT, the DOT is going to demand that you stand behind the bid. Sometimes it happens that when the bids are open, the low bidder maybe is $1 million and everybody else is over $2 million. And the low bidder says, I don't want to do the work for $1 million. It's clearly worth a lot more. I made a mistake. I'm just not going to do it. Give the job to somebody else. Well, what DOTs do is, in that case, they make the low bidder forfeit 5% of his bid. You bid $1 million, you don't want to do it? Fine. Give us $50,000 and we'll let you off the hook. Well, what's going to happen with a digital bid if the contractor says, oh, wait a minute, Infotext software screwed up. I put in that I wanted to bid $2 million, and they changed it to $1 million. A digital signature will prove that that's not the case, provided we can check the digital signature without using the same key that was used to create it. So provided we can check it without having the ability to forge it ourselves. That's where public key cryptography comes in. You can do digital signatures with secret keys, but as you've seen, it's not the most useful operation in the real world. Whenever you hear people talk about digital signatures, if they actually know what they're talking about, they're going to be talking about doing digital signatures with public key cryptography. Public key cryptography is very similar to what we've seen before. You have a key and you encrypt a file, the plain text to get ciphertext. You have a key, you decrypt the ciphertext to get the plain text back. But the difference is, instead of using the same key for both encryption and decryption, you use different keys. You have a pair of keys, known as a key pair, one of which is the private key that only one person knows, the other one of which is a public key that can be shared with everybody else in the world. So if something's digitally signed with the private key, anybody else in the world can say, hey, this is your public key. I know you signed it because you're the only person that has that matching private key. This is very, very useful. This is how a website, your bank website, proves to you that it isn't somebody spoofing their website. They digitally sign a proof when your web browser connects to the server that this is really somebody who has the key pair that was issued to your bank. So this is how asymmetric encryption works. Similar to before, plain text gets encrypted with a key to be ciphertext. Ciphertext gets decrypted with a key to become plain text, but they're two different keys. The public key and the private key always operate as a pair, and they're mathematically related. And it is mathematically possible to derive one given the other, because they are mathematically related. However, it is not practical. The amount of time the calculation takes would be longer. The sun would have long since burned out. That's how the core of public key cryptography works. You have something that mathematically is invertible, but in practical matters isn't. So you have to create the two keys together at the same time, because you can't create one and then figure out the other. So in lab 3, we're going to start by creating a public key cryptography key pair instead of an individual key. We're going to export those two keys in the pair, the public key and the private key, into form elements so that, for example, the public key, we could publish it, tell the whole world this is my public key, and then we can use the private key to sign stuff, and anybody else in the world can say, oh, I know it was you because I was able to verify it with your public key. So we're going to sign the file with a private key, and we're going to verify a signed file using the signature and the public key. Let's take a quick look at the application. And again, this application is not necessarily the best user experience in the world. We're going to generate a key pair. That creates a public key and a private key, and both of them have been exported and base64 encoded and stuck in the appropriate text boxes here. Notice that the private key is longer. Then we're going to choose a file to sign. And let's see. Do I have just a simple little text file? This is the standard, the Web Cryptography API standard. So I will choose that file and digitally sign it. And the base64 encoded signature is right in here. Now, let's say some nefarious person goes in and edits that file. And changes the file, which is a web page, which somewhere in here said that has a date. So I want to change the date in here. There. I'm going to change the copyright to 2016. Now, we give that digital signature and the file to somebody and tell them, here's my signature, verify it. The verification will fail because the file was altered. If I go back and change that copyright back and don't inadvertently do anything like changing all the line endings from Windows till Unix are back, then I can choose the file I changed back to the original one. And apparently I did change other stuff other than that 1 byte because it's not valid. So let's go ahead and pick a different file like this image, sign it. Now choose the same file back. We've still got the digital signature in the screen, verify it, and it tells us it's a good signature. Okay, as I said, this is the core of being able to keep a file that for years to come you can prove was not altered, that is, it cannot be repudiated, and who created it, the person who holds the key. Now to do that, when a person creates a key pair, they've got to promise to not share their private key with anybody, and they've got to give you their public key along with proof of their identity that you've just got to keep later to do the verifications.
How many years to come?
How many years?
Yeah, you said for years to come.
Well, there are cases with disputes over highway construction jobs that happen 10 or 20 years down the road. So if somebody wants to argue in that dispute that the contract that was signed didn't actually say what people now claim it says, you'd want to be able to verify the digital signature 20 years down the road and show that that really is the contract that they agreed on to go into court with.
I know how long digital signature is secure for.
The digital signature is good forever. How long it's secure for depends on how good computers get. If you do a digital signature that's fairly short, somebody can use brute force to figure out a matching private key and start forging the signature. The recommended length size for keys that use the RSA algorithm, which is the algorithm we're going to use, stands for Rivas, Shamir, and Edelman. The recommended length now is 2048 bits. And that's probably good for existing documents for 10 or 20 years. 5 or 10 years from now, they're probably going to tell you to use 4096 so that your files will be good for an even longer time going forward. Yes?
Is there any use for this patch file? I assume that it didn't work because at some point you read the date timestamp for the file.
It didn't work because when I saved the file, I probably changed line endings from carriage return line feed to just line feed, or in other words, I changed bytes, not just text. So if you want to digitally sign text, you're also going to have some canonical way of representing the text, so you know that you don't change stuff that isn't visible to users, like maybe trailing blanks on lines. Yes?
What would be the best way to upgrade keys in the future when encryption does?
I'm sorry, a little louder?
So, what would we do in the future when we have to upgrade the keys to ensure that people can't forge it when you're done?
What do you do when you've got to upgrade keys? You decide that the length keys you've been using all along aren't good enough, or you decide that the user's been using that key long enough that you're afraid that they might have inadvertently been careless with it and somebody else found it out. You want them to get new keys. Well, you've got two options. Either way, you start by having the user on their own machine by themselves create a new key pair. So you give them a program that creates a key pair that they're in control of. They can't create the key pair on your server or your machine because you could steal their private key when it was created. They've got to do it on their machine. They've then got to provide you with the public key, and you've got to have some way of associating that public key with that user's identity, knowing who it came from. And the two options are however you did it the first time. They can, for example, show up in person, show you their driver's license or passport, and say, here's my key. Or they can do something like, to verify it, we have them send us a copy of their picture ID and give us a phone number so we call them and verify their identity. Or you can actually use their existing identity verification to do the new one. In other words, I created a new public key, I can digitally sign it with my old one that I verified my identity with, and now that verification moves forward. So there's a couple of options. Regardless of how you do it though, users are not happy with it. They don't like doing that rekeying. But it is possible. Our service, BidExpress, has been live since 1999, handling highway construction bids. It's handled over $1 trillion of bids so far. About 43 of the 50 states use it for most or all of their bids. And there hasn't been a case yet where a bid wasn't openable or a contractor repudiated it and said that wasn't really my bid. All right, so what are the mechanics here? Well, if you want to generate a key pair, you use the exact same method that you used to generate a regular single secret key, the generate key method. But instead of saying, I want to generate this for an AES CBC key of 256 bits, you're going to say, I want to generate this for a particular kind of public-private key pair, namely RSA, SSA, PKCS1, v1.5. That has been around for over 15 years now. That is the algorithm that most web server certificates use to sign the certificate. It's not a bad choice. It has some theoretical weaknesses where people are suggesting going forward use a new slightly modified version of the algorithm called RSA PSS, but it's not widely available yet. So we're going to stick with the best thing that's widely supported. And it's also such an easy name to remember, RSA SSA-PKCS1-V1_5. And it's obvious why you would have an underscore in one place and dashes in others. This is based on, as I said, the RSA algorithm. That's the actual mathematical algorithm at the foundation of it. And this is the version of it that's used for signing. There's another version of algorithm that's used for using the same kinds of keys for encrypting and decrypting, and that's called RSA OAEP. There are other algorithms. You don't have to do RSA. There are algorithms based on, for example, elliptic curves. The API does support them, but the browser support is still kind of spotty. So we're going to stick with RSA for now. The promise, when you come back, instead of giving you a crypto key, gives you a new kind of data element that we haven't seen before. It's a crypto key pair. There's nothing magical about a crypto key pair. It's just a JavaScript object with properties named private key and public key. Each of those are themselves crypto keys. So, yes?
Quick question on the elliptical, the ECC, right? Elliptical curve cryptography.
Mm-hmm.
I've heard that they use it in mobile devices because the key length can be smaller.
Yes. One advantage of using elliptic curve cryptography is that the length of the keys is smaller to be equivalently secure.
And they claim that mobile devices use them quite often because I guess they've got the compute power for it. Do you see it in the mobile world, or do you still see it in the desktop browser?
You see them at both places, but they're not as common as RSA. But yes, if you want to use it, and I have seen some applications that use it just so that people can share the raw public keys more easily because it's shorter. You know, the keys for RSA are very long, but in my opinion, nobody's going to be able to share a key without actually passing a file back and forth. They're not going to read it out loud to each other anyway. All right. Now, in order to do this, we're going to generate a key pair, and remember I said this, we saw the application exports those keys and puts a base 64 encoding of the exported keys in the form. So that later when you say encrypt, it pulls that back in. And the reason we're doing the exporting, we don't have to do that to do when you say sign or verify. We don't have to export it to do that on one machine. We created the key pair, we can do those operations on that machine. But if we want to create a file, sign it, and have somebody else verify it, we've got to give that other person our public key. We need to export the public key to a format that we can then put in an email or something so somebody else can reload it. That's why we're exporting the public key. The reason we're exporting the private key is the private key represents me, not necessarily this web browser. I have several web browsers on this machine. I might want to be able to take this private key and use it on different web browsers. Now, when we imported and exported AES keys, we used the raw format. Raw format is only usable for secret keys. The formats that we use for public keys for import and export is called SPKI, and the format for private keys is called PKCS8, for the obvious reasons. Actually, these names have been around for a while. SPKI stands for Subject Public Key Information, and if you've ever seen a web server certificate, that certificate includes a public key in it, and the format that the public key is in the certificate is SPKI format. If you've ever run your own Apache server, you've had to also have a private key set up for the server to use for SSL. The format of the private key is PKCS8, for Public Key Cryptography Standard number 8. There are other formats available. In fact, there's a more modern one where instead of just producing an array buffer for the exported key, it produces an entire JSON object that tells the different parameters of the key. Because the fact is a RSA key actually has multiple pieces in it that have been encoded together into these other formats. But we're not going to use that. We're going to continue to use array buffers. Again, support for JWK is kind of spotty, except on Safari. Safari only supports JWK right now, which makes it a little hard to go between Safari and some of the other browsers. For the RSA algorithm, when you want to specify a key, with AES you need to tell the length in bits. With RSA you need to tell it the modulus length, which is basically the length of the key. There's a couple pieces to a key, but the part that's really the key people work with is known as the modulus. And we're going to use 2048, that's the recommended size nowadays. Then there's a public exponent. An RSA key pair is created by using two relatively prime numbers. One of them is a public exponent, the other is generated as a private exponent. And everybody uses 65,537 for the public exponent. And there are a couple of reasons. It's a good choice. It's large, but not too large. Its binary representation has only two 1 bits, which means arithmetic can be done more efficiently. But the practical reason is most of the native crypto libraries enforce that restriction. They say, we only wrote our code to handle this public exponent. Given that I'm always providing it, I don't know why they even make it a parameter, but it is a parameter. And then the hash function we're going to use for signing. And we're going to use SHA-256, which is a modern, good hash function. So in order to do signing, remember we would have already done the generate key and had those exported keys sitting in the form. So in order to do signing, we'll take the private key and import it to the crypto key, set up a file reader, and on success of the file reader, call the subtle crypto's sign method to produce a digital signature and put that encoded signature in a form element. For verifying, it's pretty similar. You're going to import the public key, however, set up the file reader, and when the file reader is finished, we're going to pull in the signature that's in a form element and send the signature and the file and the public key to the subtle crypto verify operation in order to find out if the signature is valid or not. Let's see, there's some question people asked that I wanted to get to on this. Oh, if there's a key pair and one of the keys is called public and one of the keys is called private, which is which and which do I use when? Well, the reality is either key can be used as public or private. The key generator decides that for you. It creates two keys that are mathematically related and it says, here's the public one, here's the private one. Now, when you think about the operation, you need to decide, given that operation, which key should I use? Well, if you want to sign a file, it should be signed by just one person, but the signature should be able to be verified by anybody. So you're going to sign it with a private key because only one person should have the private key, and you're going to verify it with the public key. The next lab, we're going to encrypt and decrypt data using public key cryptography, and it's kind of just the opposite. If you want to encrypt a message, you want to create something that only one person can ever read. But when it comes time to decrypt it, you want anybody in the world to have been able to send you a secret message. So the encryption is done with the public key, and the decryption is done with the private key.